Good. Are we on?
Yeah.
Okay, good. All right. So we're back. This is now for like 9th period and 6th period people who are just home, chilling on the couch, drinking lemonade. We have solved the area problem. We have then decided, no, actually, wait a minute. We didn't really solve the area problem. We just solved the polynomial area problem. We talked about how we can have rectangles with unequal widths. Now let's just take another closer look at this entire area process. So, all right. I would like to do this like just in general. I want to talk about, I guess, the area between f and the x-axis on the interval a, b. And for keeping it simple, let's just assume that that f is positive on that interval. Okay. All right. So we have seen. Question?
No.
Okay. All right. So I will draw, and I'm just gonna draw kind of like a generic function.
Continuous.
Yeah, continuous and that kind of stuff. That's probably important too. Assume f is positive and continuous. Yeah. Something like that. Okay, wonderful. And now over here. So what are our options for doing this? Oh, how many? Let's just like talk it out. How many rectangles are we going to use? N. So let's use n rectangles, and let's also just assume like equal width subintervals. So I'll just say n equal width subintervals. And okay, in that case, what is delta x, the width of each subinterval?
It's b minus a over n.
I think he is right. Yeah. If we're going from a to b, then we do b minus a is the total width, and then we divide by n. Okay, cool. All right, good. So what's one way that we could do this problem? What are the basically two ways we've talked about so far?
Formulas.
LRM and RM. Yeah, that's right. LRM and RM. This is just in general, right? So okay, so let's do it. If we are going to use, what should we do first? Let's do RM first. If we do RM first, let's kind of like make some rectangles here or whatever. Some number of them. So I now do my happy RM. La, 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 la. Basically an art class now. Rectangle drawing. Not as much as all right. So we have a bunch of rectangles. There they are. They are wonderful. Now let's write out an expression for this sum. In fact, okay. So what is this point right here? Yeah, I kind of like what Ben's doing. He's just like, it's kind of annoying to keep saying b minus a over n over and over again. So let's just call it delta x for the time being, and we know that that's what delta x is. Okay, so this is like a plus delta x. And that's like the first number that we plug into the function to get the height of the first rectangle. And then the next one, a plus 2 delta x, and then like a plus 3 delta x. Like etc. Okay, cool. So I could even write this as like a plus 1 delta x, and then we kind of do dot dot dot, and we get to the last one. What's the last one according to our sort of pattern? A plus n delta x, and keeping in mind that delta x is b minus a over n. Guys, with me, like the n's cancel, you get a plus b minus a is just b, which is exactly what it's supposed to be. So it's all like looking good. Okay. Are we like tough enough that we could just go straight to the sigma notation for this? I think we are. So we're doing RM. So what is this? This is the sum from I equals 1 to n.
F of a plus f of delta xi.
Yeah, the ith rectangle is going to have height f of a plus I times delta x, and the width of the ith rectangle will be delta x. James, you okay?
Yeah, I was just a little confused about I, right? But it's just like, I think it's...
I is just the increment, it's just the summation.
Yeah, exactly. Yeah.
Okay, good. Yeah, I think that's right. Okay, and now I'll just sort of like redo this whole problem over here. Now I will use LRAM. What's wrong? Nothing. Okay, I didn't hear what you said. All right, good. So now I will use the left endpoint of each interval. Oh, would someone like to comment on the whole like underestimate, over-underestimate thing? Well, first let's look at one thing at a time. So I get this. So that's like looking beautiful / ugly. This one is slightly trickier. What is the sum now? There's a couple different ways to do it. Who hasn't talked yet today? Maybe everyone. No, you, Justin. Yeah.
Sum is I equals 0.
Yeah, that's one way to do it, at least. Yep.
And minus 1.
Yeah, he's got this under control. Some people find this kind of tricky, right? Because think about what we did. We said, all right, it's still true that this point is a plus delta x. It's still true that this is a plus 2 delta x. But if you look at our rectangles, the first rectangle has height like that one, right? So it's that first thing, which I might even call a plus 0 delta x if I wanted to be that kind of guy. That is the number that gets plugged into the function to determine the height of my first rectangle. And then what's the last rectangle? Yeah, the last rectangle has height, whatever you get when you plug a plus n minus 1 delta x in. So everyone see that? Okay, good. All right, so Justin, I think you were on the right track anyway, but now everyone sees what we're talking about. So we start counting to 0, and we stop at n minus 1, and this is
F of a plus I times change in x times change in x.
okay. So good. All right. In general, are these going to be equal to each other? Oh. Yeah, I might have screwed up and asked the wrong question. Yeah, in general, these are not going to be equal, right? They're a little bit different. And yet, the more rectangles you take, the less that difference is going to kind of disappear, right? And neither of these is necessarily an overestimate or an underestimate because the function is both increasing and decreasing on the interval. But this seems very, very reasonable, and yet it's true. If you take the limit as n goes to infinity of each of these, they are the same. Yeah, that's like true. Okay, and actually that is just a special case of a sort of more general and even more abstract theorem, which says that, well, okay, there's sort of another kind of rule. So before that, I'll just introduce some notation. What I'm now going to do is I'm going to look at each subinterval at a time. So I'm going to go on a subinterval by subinterval basis, and I'm going to look at that subinterval and be like, yo, where's the function big and where's the function small? So let m sub I be the x-coordinate of the minimum value of f on the ith subinterval.
You're in the print. But you're not in the lecture, so you're fine right now. I'll tell you when you need to go.
And let big M sub I be the x-coordinate of the maximum value of f on the ith subinterval. Now I can pursue these like sort of alternate methods to find the area under the curve. They are known respectively as the min rule and the max rule. So give me a second to first draw some cool functions. Not that cool actually. Okay, so here are some functions. And now the goal is to find the area under those curves. But now I pursue first the min rule. The min rule says, yo, split up this function into subintervals, and on each subinterval, take the minimum height rectangle. So like on this first subinterval, for example, what point on that subinterval should I use? The left endpoint, right? Yep. So I draw my rectangle like so. Oh yes. Next subinterval, what should I use? It's hard to tell, but I guess it's the left, yeah. Okay, now what should I use? The like right. Cheating a little bit for clarity. And then on that fourth subinterval, what point should I use? That like relative minimum, yeah. So, cool. Okay. So in each subinterval, I chose like the smallest rectangle possible. And then, of course, we have the max rule. And the max rule is just basically a similar kind of thing, right? We go, So now on this first subinterval, I will choose the right endpoint. On the second subinterval, I will choose the relative maximum. Oh yes. And the next subinterval, what should I pick? And then the last one. Okay. All right. This is very interesting. Thoughts about what we have just done? What are your unstructured, what's your emotional reaction?
Cool.
Cool. Yeah, that's good. Yeah. No, Gleason.
It's kind of like look a lot more like the real one than the others do.
Okay. Okay, good. All right. How about some more specific mathematical thoughts? Mathematical thoughts, please. There's a couple interesting things to say about this process. Talk about the min algorithm and the max algorithm. What? So we've done them. So what? Catherine, do you have a comment? Thoughts? No? Nothing? Please.
Well, I'm noticing that the min is a much less and the max is much more versus LREM and RM, one of them's greater than one of them's less than, but they're both would likely be closer than the min and the max are.
Okay.
To it.
Yeah. More things we can say. Yeah.
So min is a minimum bound of the area, could actually be, and max is an upper bound.
Yeah, that's kind of obvious, but definitely worth mentioning, right? The true area must be somewhere in between the what you get by doing the minimum, what you get by doing the maximum, right? Okay, so that's important, right? So this is a lower bound on the area and an upper bound on the area. Yeah. How about another thing? Anyone else have anything to say?
Can you give a hint?
Donna.
I guess when for the min, when the function is increasing. It's
Okay. More general. Yo.
This is more like a general question. Why don't we give them triangle hats?
Good night.
Wait, averaging them.
You spontaneously said it over here, or you did because I asked it. What happens if I take the limit as n goes to infinity?
They're the same.
Yeah, they're the same. Okay, then that's definitely worth mentioning, right? This, I'm definitely going to get different things from the min and the max for a particular n. In fact, I can write this out, right? The min is the sum from I equals 1 to n of, what's the area of the ith rectangle? Well, it's like f of little m sub I delta x, right? Because that's how I define little m sub I, to be the x coordinate, the point on each subinterval where the function is smallest. And over here, I'm going to get the sum from I equals 1 to n of f of big M sub I times delta x, because that's how I define big M sub I to be the, to be on the ith subinterval. These are generally going to be different, but claim if I take the limit as n goes to infinity of both of these, then these are the same. Okay, this, I am not going to prove this. This is true. This is like a theorem of advanced calculus. And if you take some advanced calculus class sometime in your future, you will prove this with some nightmare epsilon n argument involving, yeah.
Why is it not just squeeze theorem?
So the squeeze theorem, you have to have some two things to squeeze it between, right? So I hear what you're saying. You're sort of saying,
Like, that one's a minimum, that's a maximum. The limit's always between them. And the limits are the same, so.
right. Well, how do you know the limits are those limits are the same? That's what we have to
Oh,
prove.
right.
Yeah, right. That's what we have to prove. Yeah, he's kind of doing the opposite. In fact, what he's talking about, we're going to do right now. Because what he's saying is, if we accept it on, not faith, but common sense, that this is true, then what that means is that we can actually use any number we want, right? So now we're going to generalize this process in yet another way. Also, if someone could erase that backward, that'd be awesome. We're going to generalize this process in yet another way by saying, yo, we don't even have to, what's wrong?
Should I move the camera?
Nah, just like turn it, whatever. We don't have to use LRAM. We don't have to use RRAM. I don't have to do the minimum. I can do the maximum. I can just pick whatever point I want. So let x sub I star be an arbitrary point. An arbitrary point in the ith subinterval. In other words, just pick any point whatsoever that you want on that subinterval. And pursue this algorithm of just using that point. And in fact, this is kind of what Naveen was talking about, which is like, let's just state some obvious facts, right? F of x sub I star is guaranteed to be between f of little m sub I and f of big M sub I. Because that's just kind of the definition of little m sub I and big M sub I, right? This is the point on the ith subinterval where the function is smallest. This is the point on the ith subinterval where the function is biggest. So if I pick any point whatsoever, then its y value will be somewhere in between. Yeah? Okay, now what? Building this up slowly. This is it, yeah.
Squeeze theorem.
Almost. First, multiply by delta x. Okay, if I multiply by delta x, then, you know, I still have a true statement. But now this is a statement about rectangles, right? It says that the area of a rectangle drawn at an arbitrary point on the ith subinterval, long sentences here, is somewhere in between the minimum area rectangle and the maximum area rectangle, which makes complete sense. Cool? Okay, and as this is true for every subinterval, now add them all up. So, exactly, summation. If that's true for each one, now I take the sum from I equals 1 to n of f of m sub I delta x is guaranteed to be between the sum from I equals 1 to n of f of x sub I star delta x, which is between the sum.
There's no door between these, Mr. Rose, I don't think.
Okay, good. Less than or equal to. Yeah. Good. So now what is this line saying in words? It basically says, yo, if you follow this process of picking whatever point you want, plugging that into the function and taking that rectangle, and you do that over and over again, what you're going to get is certainly going to be in between following the minimum rule and following the maximum rule. Cool? And now,
Just saying that there's a minimum and a maximum, basically.
So,
what we have now done is kind of just proved what we sort of said over there, right? Which is that the true area will be somewhere in between. Or at least this is in between, yeah.
Wait, you said it was like a really complex proof. Like,
I think this is a complex proof. I haven't really thought about this too deeply, but I think proving this would be hard. But now, this is kind of what Naveen was getting at, I think. Now I can apply the squeeze theorem. Because remember, the squeeze theorem says if you have some function and you know it's in between two other functions, if these two have the same limit, then this one comes along for the ride as the prisoner, right? And so by the assumption that when you take the limit as n goes to infinity, so I'll just write, if you take the limit as n goes to infinity, and you also take the limit as n goes to infinity here, and you get the same number, which is what I told you does happen, then we know by the squeeze theorem that when you take the limit as n goes to infinity here, you also get the same number. Cool, cool? Okay. All right. That was a very theoretical conversation. Basically, here's the gist. What we have learned half an hour ago is that this process of finding the area under a curve can be generalized by possibly, if you want to, taking rectangles of unequal widths. What we have now just learned is that this process can also be made more general by choosing, even within each subinterval, whatever point you feel like on that subinterval, and you're always going to get the same thing. All right, it is now time to introduce a sort of name for this whole process. These are called Riemann sums. All right, so what are Riemann sums? Basically, Riemann is like a German mathematician, Bernhard Riemann, 19th century guy. What's up? We can't call him Riemann, that would be weird.
Why not?
Really lucky though with the famous people who discovered this formulas didn't have really generic last names.
The Smith sum.
Yeah.
This like that happens a lot, right? I don't know. All right.
They're probably not on agreement.
Good. Okay, so Riemann. What is a Riemann sum? A Riemann sum is all these sums that we've been doing over here. It's difficult to give like a very, very formal definition of this, so instead I'm just going to kind of list it out in bullet points. Ready? Here's what you do. Take a continuous function on a closed interval. So take a continuous function f on a closed interval AB. All right. And now, as we talked about 45 minutes ago, you can partition up this interval in any way you choose. So like, I'll just say, partition that interval. All right. And it has to be a good partition. Yeah, we're going to get that. So, yup.
Wait, can you repeat what?
I will do that in 1 second. So I have the interval AB, so it's just like a number line, right? And the idea is, probably most of the time you'd want to just split it up into equal width subintervals, but if you want to do something weird, feel free to do so. So you could like split it up according to some strange complex formula or whatever, and you could call this like x1, x2, x3, x4 is what people do, dot, 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 and then this is like x sub n, assuming we have, n of these. And then A, we can even call that x of 0. So this is like an example of a sort of generic partition. And Noah says, make sure it's like a good partition. So make sure it's a good partition. And a good partition is one in which, as n goes to infinity, even the widest subinterval goes to 0. Okay, cool. Okay, this is kind of a theoretical point. All right, having done that, now choose a sample point, x sub I star, from each subinterval. Well, from each subinterval. Okay. And finally, you put it all together. So you go to the ith subinterval, you plug into the function that point, x sub I star, you multiply that value by the width of the ith subinterval, and then you sum them all up from I equals 1 to n. This thing is called a Riemann sum. In words, a Riemann sum is the sum of products of widths of a good partition, widths of the subintervals in a good partition, times the values of the continuous function at a sample point drawn from each subinterval. Okay, yo.
I didn't really get the good partition.
It's not that important. It's like really not. Also, I think I spelled partition wrong.
Partition.
Yeah, just like, okay, good. All right. Now we are ready to introduce one of the most important concepts of the entire analysis 1A, integrals.
I would roll part of our.
Yeah, okay.
I already made that.
What are integrals? They are these guys as n goes to infinity. Integrals are actually these things that we've been doing for basically the last 3 days. More specifically, an integral is the limit as n goes to infinity of a Riemann sum.
Wait,
Okay, yes.
did Riemann know about integrals?
Yes, Riemann came like 200 years after Newton, so it was another one of those situations where, kind of like with derivatives, where people were doing it sort of like informally by just drawing pictures and hoping for the best, and then Riemann kind of like tightened it up and defined it in this like formal way like this. Good question. Okay, so without further ado, the integral. Whoa. The integral of f from x equals a to x equals b, and there's some notation for this. The notation looks like this. There's this weird curly s thing, and then you put an a here and you put a b here, and then you write the function, and then you put this little dx thing there. All right, so like what is, I've never seen, I don't know about you. So the integral of f from x equals a to x equals b is, by definition, the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I star delta x sub I. Okay. And these, before we talk about this anymore, I'll just introduce a little bit more vocab. These little things have names, right? So this guy, these are called the limits of integration. They tell you where to start integrating and where to stop. This is called the upper limit of integration, and this is called the lower limit of integration. And this function that you're integrating is called the integrand. Okay. So yeah, it's like it's like Latin. It's like a silly word. Okay. So all right. So what's going on here? It's like this. Catherine, check it out. Say you want to do an integral. All right. Of a particular function on a particular interval a, b. Step 1, make sure your function's like continuous and stuff. Then take that interval, split it up into some kind of partition. Use equal with subintervals or not. Then pick a sample point from each subinterval, multiply the value of the function at that sample point by the width of that subinterval, add them all up, take the limit as n goes to infinity, that's an interval. Oh, I should mention, provided that this limit exists. Provided the limit exists. If you had some crazy function where the limit turns out to not exist because it goes up to infinity or something, then maybe you don't, then the interval's like undefined. Okay, cool. This is like awesome. Also, this bit of notation is like genius because each piece of this symbol reminds us of its like humble origins as a finite Riemann sum. Right? An integral is what you get when you take the limit as n goes to infinity of a Riemann sum. And so, piece by piece, you sprinkle the magic calculus pixie dust onto this side, and you get this side. Note, this happened last quarter as well with derivatives. Right? We had this notation dy dx, which we agreed was like awesome, because after all, what is the derivative? Well, it's like the limit as delta x goes to 0 of delta y over delta x. Delta y is like an actual quantity, the change in y. Delta x is also like an actual quantity. So this is like a fraction. And then as delta x goes to 0, you sprinkle the magic calculus pixie dust on this, and delta y becomes like infinitely small, and delta x becomes infinitely small, and you get like dy over dx. Okay, the same thing happens here. It's like Cinderella. In Cinderella, the crucial scene of Cinderella, in my opinion, is when the fairy godmother, that's me, comes in and gets Cinderella ready for the ball. And in the Disney version, canonical Disney version, she sprinkles the magic calculus pixie dust on the pumpkin. The pumpkin becomes, yeah, you didn't know that this is about calculus. No, it's actually about calculus. The pumpkin becomes a coach, and then she sprinkles the magic calculus pixie dust on the mice become the horses. Yeah, wait, it gets complicated. Wait, the mice become the horses. Then there's there is also a horse, which is confusing. Which, when you sprinkle the magic calculus on the horse becomes the driver of the. So that's an interesting role reversal there from the horse's perspective. There's a dog who becomes the coachman that opens the door for her or whatever, and then various other things happen.
She gets a dress.
Good. Okay, good. So, wait, there's a point to this story. Also, well, I'm going to leave that on. Alright, so watch as I sprinkle the magic calculus pixie dust on this Riemann sum, and it becomes an integral. So, okay, here we go. For starters, there's this delta x, which is like, this is pretty exciting. This is a width of a subinterval, right? So this is like an actual quantity. It's like a width. It's a delta x. When I sprinkle the magic calculus pixie dust on it, as n goes to infinity, what's happening to these widths? Well, they're becoming smaller and smaller and smaller. Oh, they become eventually infinitely small. Hence the little dx. That's what that dx means. It's an infinitely thin subinterval. Okay, now I'm taking sample points. How many sample points? A lot. Like 1,000, 1,000,000, 1 billion. As I sprinkle the pixie dust, as n goes to infinity, now I'm sampling this function like infinitely often. And it becomes, the continuous function f of x, which you can think of as being sampled like infinitely often. And finally, this sigma, which represents sum, as I sprinkle the magic calculus pixie dust on the sigma, this is the most Cinderella-like of them all, it kind of like straightens out and becomes the curly s. S for sum. This is supposed to represent like infinite sum. Okay, cool. So you should like look at the symbol of the integral and think sum every time. Okay, this is great. Should we do some integrals?
Yes.
All right, here we go. I got some intervals for you. Do them.
Yo, it's gonna be like the derivatives. We're gonna do it.
Take the integral from 0 to 5 of x. And we got more over there. You guys know what to do? No. All right, better talk to the person next to you then.
I'm so confused. What? No, the person's drawing it back to the wall. We have new neighbors. Hi, neighbors.